BigSoftEd presents long multiplication. There are many situations where you might find it helpful to multiply two large numbers together. You might be doing a spot of DIY, calculating the true cost of that long-term payment plan on your TV, or totting up the hours lost after binge-watching TV shows for 6 weeks. Hey, I'm not judging. Or maybe you just want to find out how many packs of Shouty Crackers you impulse purchased in that online deal of the day. To calculate any of these with pen and paper, long multiplication is a good choice, but other methods are available. But why is it called long multiplication? Does it take a long time?
7.5 million years.
Does it need a long sheet of paper? Or is it just that it can handle long numbers? It shouldn't really take a long time, as long as you know your times tables and have had some practice. A calculator is quicker, providing you can find one, either in the house or among all the apps on your portable device. Arguably it takes no more space than other popular methods. But yes, it most definitely works well with long numbers. It also works quite well with decimals. But we're not going to cover that here. What multiplication is? Rather than write out all those add 4s, we can instead write that there are 5 lots of 4. If you've seen the BigSoftEd video on chunking, or if you were already very smart, you'll know that multiplication can be called repeated addition. For example, 4 times 7 means 4 lots of 7 added together. There are 7 apps on each row of this screen and 4 rows, so to find out how many apps there are altogether, you can count up in 7s. Even better, commit the answers to simple multiplications like this to memory. This is called learning your tables. This table, in fact. You should memorise it for efficiency. Not being able to pluck answers to common multiplications from your brain means methods like long multiplication, long division, chunking, and just about any other mathematical shortcut will be as slow as treacle. It's like trying to play a piece of music, but having to look up what each note is every single beat.
Oh, I'll never get it, never, oh!
If you haven't learned your tables, don't be daunted by this thing. You only have to memorise a little more than half of it, as the shady parts are the same. Here's a clue as to why that is. This is because multiplication is commutative. This means it doesn't matter which way round you multiply the numbers, the answer is the same. It shouldn't be too hard to see why. Multiplication isn't the only operation that is commutative. Which of the others is too?
Pause for thought.
As well as being commutative, multiplication is also distributive. This isn't an excuse to throw out multisyllabic words, because I have problems with multisyllabic words. The distributive property is what allows long multiplication to work. In fact, all of these methods make use of it. You see, if you wanted to know how many chairs there were in 7 rows of 16, you'll probably find your times table stops short of the 16s. Most people learn no further than 12 times 12. Distributivity to the rescue. You can split 16 into 10 and 6. 7 times 10 and 7 times 6 are in the times tables. The distributive property means if we add these two answers together, we get the answer to 7 times 16. In fact, you can split the 16 any way you want, into as many parts as you want, and even use negative numbers. Oh, and if instead we wanted to know how many chairs in 16 rows of 7? So we can use this distributive property to help with harder multiplications. A problem like 17 times 26 can be split into 4 easier multiplications, and those 4 answers added together give us the answer to the original problem. In fact, a way of multiplying larger numbers, sometimes called the box or grid method, does exactly this. It's a pretty good alternative to long multiplication. Of course, you quickly find you're having to multiply numbers outside of your times tables with this method, but there are simple maths tricks you can use to deal with them. Namely, ignore the zeros, multiply the numbers left, then put as many zeros at the end as there were in the numbers you multiplied. It's easier than it sounds. Once you have an answer in every box, add them all together, and that's the answer to the multiplication. But with larger numbers, there are many more zeros popping up all over the place, like Cheerios in a bowl of milk. That can only lead to mistakes and a hankering for cereal. An improvement is what's sometimes called the Lattice method. It cleverly does away with the Cheerios by using a Shreddies-like lattice. This is both its strength and its weakness. If you're okay drawing the grid, you'll probably like this method, but if all your written work looks like you wrote it on the bus, you might find difficulty drawing the grid, and time consuming if you make a mistake. But it does have some advantages over long multiplication. You don't have to know a times table past 9 times 9, and you can work out the multiplying parts in any order you want. This also means it's easier to pick up where you left off if you get distracted.
Oh, I'm sorry, did I break your concentration?
Checking your work is easier too. When the multiplying's done, you add up the numbers in the diagonals, carrying as usual. One odd thing about the lattice method is how the final answer appears. It's bent round the corner, which might seem a little weird. Still, a very good method for multiplying large numbers. Long multiplication doesn't bother with grids of any kind. It suffers a little with an attack of the Cheerios, but as long as you keep everything in columns, most of them will be stacked neatly together like a log pile of Cheerios. Squared paper helps. As does this software, available for free from the BigSoftEd website. Let's solve a problem using long multiplication. Just like with the box and lattice methods, in long multiplication you have to multiply every digit in one number with every digit in the other number. But unlike the others, the lack of a grid means it's down to you to remember which digits you've multiplied. So it's important to get into a routine. This software offers some assistance in tracking where you're up to in the question, but you should be able to solve questions without it. The first step is to set up the question. Write the numbers one above the other with the unit digits in line. Purists would say the second number should go on the bottom, but the commutative property means you'll get the same answer whichever way round you put them. Usually you'll want the smaller number on the bottom. Now we can start the solution. Start with the unit digit in the bottom number and multiply it with each digit in the top number from right to left. Record each answer below the line, writing the units in the next available column and carrying any tens digit. If there's a carried number from the previous answer, don't forget to add that on. For the last multiplication in the row, just write the tens digit full size in the next column. Once that's done, move on to the tens digit in the bottom number. Because it's the tens digit, you need to put a 0 in your answer first. This is the part most people slip up on in long multiplication, forgetting the 0. The 0 takes care of the fact we're multiplying by 30 rather than 3. Carry on the same as the previous row. 4 times 3 is 12, 7 times 3 is 21, plus the carried digit makes it 22, 6 times 3 is 18, plus the carried 2 makes it 20, which we write full size because it's the last multiplication. Once you've multiplied all the digits, you're ready to move on to the final part of long multiplication, adding up your answers. 8 and 0 is 8, 4 and 2 is 6, 3 and 2 is 5, 1 and 2. When the adding is done, you have your answer. Here's another question partly solved. I've just finished working out the second row of multiplications, but this time the bottom number has 3 digits, so I've got another row of multiplications to work out. Before I do that, as it's the hundreds digit, I have to put in 2 zeros. The trick to remember is that your first answer in each row must be in line with the digit you're multiplying by. Everything to the right of that should be a 0. In fact, some people skip the zeros altogether. These people are either very neat or very foolhardy. Whether you're neat or not, put the zeros in. It's what they were invented for. Notice what each row of multiplications is showing you. They are the answer to 3 simpler multiplications. Is the distributive rule at work? The more rows of multiplication you have, the trickier the addition is at the end. Make it easier by looking for pairs or groups of numbers that add up to 10. In this question, which number would you put on the bottom? It won't make any difference to the answer, but it does make a difference to the amount of working out you have to do. Usually you want the smaller number on the bottom, especially if it has fewer digits. This is because you can expect to have 1 row of multiplying for every digit in that number. 2 digits means 2 rows, 3 digits 3 rows, and so on. But if one of those digits is a 0, you can skip that row entirely. That's because whenever you multiply anything by 0, the answer is always the same.
You get nothing! You lose!
That row altogether. No sense putting in a row of zeros. Skip to the next digit. Just remember to put in the correct number of zeros for that row. You need to pad with zeros until you're underneath the number you're multiplying by. So in this question, you will have fewer rows of working if you put the larger number on the bottom. 3 rows of multiplication versus 4 rows the other way round. And that's long multiplication. Thanks for watching. Now go forth and long multiply.